All right, hi folks. As promised, I'm doing another example of combustion analysis. So wanted to show you guys one where we have a third element in the mix. So we'll go ahead and take a look at this one. An unknown carbohydrate was analyzed by combustion analysis. If 5 grams of the compound, which contains carbon, hydrogen, and oxygen, is burned, 7.33 grams of carbon dioxide and 3.02 grams of water are recovered. Find the empirical formula of the carbohydrate. Now, the first thing we're going to do is start by determining how much carbon and hydrogen there are, because remember in this combustion reaction, we always, all of the carbon from the unknown goes into carbon dioxide. So we're going to set up two equations to figure out these things. So we'll use the mass of carbon dioxide to figure out the mass of water, of carbon. And we'll use the mass of H2O to figure out the amount of hydrogen. The main difference here is we're also going to want to find the grams of each, because the overall compound that's burned is grams of oxygen, grams of carbon dioxide, and grams. Sorry, let me rephrase that and also write it up where you can see it. So the mass of each element is going to add up to the 5 grams. So once we find the amount of carbon and hydrogen, if we can get them into grams, we'll subtract to find the amount of oxygen. And then we can determine the mole ratios, similar to how we do for percent composition. So let's go ahead and you could pause the video if you need to jot the rest of the question down or anything, but I'm going to go ahead and start using a new piece of paper. So first, let's figure out how much carbon there is. We are told that 7.33 grams of carbon dioxide are collected. So before we can figure out how much carbon that is, let's divide by carbon dioxide's molar mass. And then we know that for every 1 mole of CO2, there's 1 mole of carbon. .33 divided by 44.01, and we get 0.166553 moles of carbon. So we don't want to round or anything yet. We're also going to need to determine grams of carbon so we can subtract from the total compound and find out how much oxygen there is. But we'll keep this moles. To find grams, we are going to multiply by the molar mass of carbon, which is 12.01. So in the original compound, there was 2.00 grams of carbon. So that's how much of the original mass was carbon. All right, next let's use the information we're given about water to find some things out about hydrogen. So we're told 3.02 grams of water are recovered. So we want to divide by water's molar mass to figure out how many moles that is. 18.02. And that gives us moles of water. But we're interested in moles of hydrogen. There are 2 hydrogens in a water molecule, so the mole ratio is also 2 to 1. And what we'll get if we run this through is 0.335183 moles of hydrogen. Now, if there wasn't a third compound, we could at this point divide by the smallest, a third element, not a compound, and then get the ratio between the carbon and the hydrogen. But we need to figure out how much oxygen was there because this compound contains oxygen as well. Because when we burn it, we're adding additional oxygen into our products, the way that we have to figure out how much there is to subtract the mass of carbon and hydrogen from the total compound. So let's figure out the mass of hydrogen from the original compound. And it's 0.338 grams. So now to find the mass of oxygen that was in the original unknown carbohydrate that we burned, we take the 5 grams of that unknown and we're going to subtract. We know it's just carbon and hydrogen and oxygen, so whatever's left over will be the mass of oxygen. 5 minus 2 minus 0.338, and I get 2.662 grams of oxygen. Now I'm going to divide this by the molar mass, because if I get moles of carbon, moles of oxygen, and then moles of oxygen, I will have, I'll be able to calculate the mole ratio by dividing by the smallest, like we do in empirical formula calculations for percent compositions, because we're trying to determine the ratio. So for oxygen, we're going to have to divide by oxygen's molar mass. I get 0.166375 moles of oxygen. So I'm going to be interested in the relationship between the moles of all my components. Just at a glance, we can see that the carbon to oxygen is going to be 1 to 1. And it looks like hydrogen is times 2, but we're going to verify that by dividing. So all of these we're going to divide by the smallest, which is the 0.166375. Let me do that in green. We divide all of them so it doesn't change the relationship, since it's a proportional kind of thing. And so for oxygen, I will get 1, technically 1 mole. And then 0.335183 divided by 0.166375. I get 2.0146 moles of hydrogen. And then the carbon is going to end up being really close to 1. 1.0011. And so now these are our mole to mole ratios, which can go in the subscripts of our empirical formula. So what we'll get for our empirical formula is C1 H2O1 or CH2O. So there's my empirical formula. And that's how you do combustion analysis with 3 elements. You could be given the molar mass of the carbohydrate and then asked to find the integer by which you have to multiply this. But it's the same method as some of the ones we've already done. So we'll go ahead and stop here. Oops, bumped that. But hopefully this is a helpful tutorial for you on how to do combustion analysis.